transmission lines and waveguides. So coming to rectangular waveguides. So rectangular waveguide. So rectangular waveguide is a combination of four conducting walls. So it is very useful for microwave transmission. So here I am going to discuss general field equations for rectangular waveguide. Impossibility of TEM wave in any hollow metallic structure. TEM wave, TE wave, cutoff frequency. So these are the general field equations I am going to derive from Maxwell equations. So here in the rectangular waveguide, I am assuming along x, along y, there are boundaries, along z there is wave propagation. So here, so these are the final general field equations for rectangular waveguide. So Ex, Ey, Hx, Hy, these are the four field components. So dou by dou x, dou by dou y represents field variation along x, along y. Along x there are two conducting walls, along y there are two conducting walls, along z there is wave propagation. So then impossibility of TEM wave in a hollow metallic structure. So for TEM wave, condition is Ez equal to Hz equal to 0. Suppose if Ez, Hz both are zeros, then all the field components Ex, Ey, Hx, Hy all are zeros. That means TEM wave is not possible in not only rectangular waveguide, in any hollow waveguide. So TEM wave does not possible. So coming to TEM wave, transverse magnetic wave, here condition is Hz equal to 0. So here first of all, so I am taking electric wave equation del square E equal to minus omega square mu epsilon E. So then assume Ez equal to xy. X is function of x only, y is function of y only. So then so here then it is the Ez equation. Ez equal to C1 cos Bx plus C2 sin Bx into C3 cos Ay plus C4 sin Ay. So here, so by applying boundary conditions, so first of all bottom conducting wall. So rectangular waveguide is combination of four conducting walls. Bottom conducting wall that is placed at y equal to 0. At y equal to 0, Ez equal to 0. Means electric field tangential to conducting wall is equal to 0 for all x from 0 to a. So then one by one, by applying four boundary conditions related to four conducting walls: bottom conducting wall, left conducting wall, top conducting wall, right conducting wall. So finally, it is the Ez equation. Ez equal to C sin m phi by Ax sin n phi by B by A is width of waveguide, B is breadth of waveguide, m comma n both are integers. M represents field variation along x, n represents field variation along y. So these are the final equations for TEM wave, Ex, Ey, Hx, Hy. So here for different values of integer m comma n, there are different field configurations possible, and these different field configurations are called as modes. General mode is TEM Mn mode. Suppose m equal to 0, n equal to 0, or m equal to 0, n equal to 1, or m equal to 1, n equal to 0. For all these combinations, all field components are zeros. That means TM00, TM01, TM10 modes does not exist. So least possible TM mode is TM11. So coming to TE wave, transverse electric wave, condition is Ez equal to 0. So here by taking magnetic wave equation, also by applying boundary conditions to the HZ equation. Finally, so these are the equations for TE wave. So here also, for different values of integer m comma n, different field configurations are possible, and these are called as modes. General mode is TE mn modes. Mn mode. Suppose m equal to 0, n equal to 0, integer m equal to 0, n equal to 0. All the field components are zeros, so TE00 mode does not exist inside rectangular waveguide. Suppose m equal to 0, n equal to 1. Some field components Ex, Hy, Hz not equal to 0. Suppose m equal to 1, n equal to 0, Ey, Hx, Hz not equal to 0. So least possible TE modes are TE10 or TE01. Coming to cutoff frequency of rectangular waveguide. So here cutoff frequency is derived from phase constant equation. Phase constant equal to omega square b epsilon minus m phi by a whole square plus n phi by b whole square. That omega equal to omega c, beta bar phase constant equal to 0. That means there is no wave propagation at cutoff frequency. So from this cutoff frequency, finally cutoff frequency equation for rectangular waveguide is 1 by 2 square root of b epsilon into square root of m by a whole square, m by a whole square plus n by b whole square. Suppose medium between two conducting plates, medium inside waveguide is free space, then cutoff frequency equal to c by 2 square root of n by a whole square plus n by b whole square. Operating frequency less than cutoff frequency, then gamma bar is purely real, there is no wave propagation. Operating frequency f greater than cutoff frequency, gamma bar is purely imaginary, there is wave propagation. Okay, gamma bar is purely imaginary means wave propagation is possible inside waveguide. So to get wave propagation in the waveguide, operating frequency f must be greater than cutoff frequency. So you can say waveguide acting as high pass filter. So from this cutoff frequency, now we are going to conclude dominant mode. What is dominant mode? The mode which is having least cutoff frequency and highest cutoff wavelength, called as dominant mode. So cutoff frequency, cutoff wavelength equations. So for TE10 mode, cutoff frequency equation C by 2A. For TE10 mode, cutoff wavelength is 2A. For TE01 mode, cutoff frequency equal to C by 2B. So out of C by 2A, C by 2B, so these two C by 2B having more value, so because A greater than B. So that means TE10 mode having least cutoff frequency, so TE10 mode is dominant mode for entire rectangular waveguide. Only to TM mode, TM11 is dominant mode, suppose only TE10 is dominant mode. Next dominant mode is TE0. So that's about dominant mode cutoff frequency.